Hello everyone, I am Seshavidya, working as Associate Professor in the Department of Electronics and Communication Engineering at R.M.K College of Engineering and Technology. So in today's video, we are going to discuss parallel adder, subtractor and then parallel adder subtractor together. So first we are going to discuss binary adder, which is also called as parallel adder. So here we are going to discuss, that is we are going to perform the addition, and then by using that binary separator we are going to perform the subtraction, and finally we are going to perform both addition as well as subtraction by using a single circuit. So let us start with the binary adder, which is also called as parallel adder. So what is this parallel adder or binary adder is nothing but it is in actually it is in 4-bit adder. Why? Because it is, so here we are going to use full adders for the addition purpose. So here we'll be using 4 full adders, so that it is also called as 4-bit binary adder. So here it is capable of adding two 4-bit numbers. And similarly, and obviously we'll be getting that output is also in terms of 4 bits. So usually if you just add two numbers, obviously we'll be getting sum and carry output. So similar way we are going to check both sum as well as carry output. So here if you just look into this circuit diagram, so this is full adder 1, full adder 2, full adder 3, full adder 4. So we'll be giving that two 4-bit numbers to the full adder as an input, that is A0, A1, A2, A3. So this A3 is nothing but MSB bit, and A0 is nothing but least significant bit, that is LSB bit. Similarly, the second number, that is B3, B2, B1, B0. So B3 is MSB bit and B0 is LSB bit. So we'll be giving both A and B each of 4 bits. So which is given to the full adders 1, 2, 3 and 4. And if you just look into this block diagram, for the full adder 1, there will be a carry in. So what is the purpose of this carry in is, so this carry output of the lower order stage is connected to the carry input to the next stage, that is next higher order stage. Okay, so that it is also called as ripple carry adder. So for this purpose, we can call it as ripple carry adder. So if you just give the two 4-bit numbers to the 4 full adders, which will give you sum as well as carry. So let us consider an example. So here consider word A, which has the 4 bits 1, 1, 1, 1. And that is add and word B, which will have the 4-bit value as 0, 0, 1, 1. So which means we are going to add A with B. Okay, so what is it? So that is a normal addition manually. 1 plus 1, it is actually 1, 0. So 0 is nothing but sum. So 1 is nothing but carry. So this is nothing but carry into the next higher order stage. So now 1 plus 1 plus 1, which is nothing but 1, 1. So sum is 1, carry is also again it is 1. So again this will act as an input carry to the next higher order stage. Now it is 1 plus 1 plus 0. So obviously it is 1, 0. So 0 is nothing but sum. Again there will be a carry input. Now the sum is 1 plus 1 plus 0. Again the sum value is 0 and carry is 1. So the final carry is nothing but output carry, and sum value is nothing but 0, 0, 1, 0. So this 0 is nothing but MSB bit. So here we will be getting S3 is equal to 0, S2 is equal to 0, S1 is equal to 1, S0 is equal to 0. And final output carry that is equal to 1, that is C out is equal to 1. So likewise any 4-bit numbers, that can be added, so that we will be getting both sum and carry out. Similarly, from the subtraction also. So this is the circuit for binary subtraction, which is also called as parallel subtractor. Why it is called as parallel subtractor or parallel adder? That is, we'll be giving two 4-bit numbers at a time. Parallelly, we'll be giving both the values at a time. So that it is called as parallel adder in the previous case. Now here it is called as parallel subtractor. If you just look into that both the diagrams, what is that difference is that? So the second value, that is add and word, that will be given in terms of, that is NOT gate. Why? Because here we are going to perform, and that is a binary subtraction by means of 2's complement. That is, we are going to convert the add and word into 2's complement, and then simply we can just add together. Why? Because in all the 4 blocks are nothing but it's in full adder, which will perform the addition. Okay, So in terms of addition, we are going to perform the binary subtraction and by using that process called 2's complement. So which means what is 2's complement? So first you have to take the 1's complement of add and word, and then we have to add 1 to the LSB bit, that is here, Cin. So this first number I am just taking as it is, A3, A2, A1, A0 as it is. The second number, that is the second value, add and value, I am taking it as B3 bar, B2 bar, B1 bar, B0 bar. So whatever the bit which is given to the B3, B2, B1, B0, that will be complemented. And at the same time, so we'll be giving that carry input Cin is equal to 1 always. So by taking 1's complement of the add and word and adding 1 to the LSB bit of add and word is nothing but 2's complement. So your second value that becomes 2's complement. Now what can we do? Now we can just perform the normal addition. So that value that will be added with the actual 4 bits. So obviously we'll be getting that sum and carry out. Okay, the only difference is that the add and value is, it is taking into consideration by 2's complement. So by means of 2's complement, we will be performing binary subtraction. So this is nothing but binary subtractor. Comes binary adder subtractor. That is in both the process at a time. So here we will be using that again for full adder. So here also we are going to perform addition as well as subtraction for 4-bit numbers. So we'll be considering that 4 full adders. So here it is, the first number is A3, A2, A1, A0. And second number, that is add and word, is B3, B2, B1, B0, which is given to the one of the input of XOR gates. So there are 4 XOR gates are connected to the 4 full adders. The other input of all 4 XOR gates are connected to the number, or we can say that data, that is M. Okay, so that M, it is also connected to the carry input of first full adder. Okay, and then from each full adder circuit, what you are getting, that output is nothing but sum. So S3, S2, S1, S0. And if you just look into this diagram, there will be one more XOR gate that will be connected to the carry output. That is the final full adder output is nothing but carry output, and that C3, the previous carry. So what's the purpose of this XOR gate is, and here we'll be getting that output as V, which is just to deduct an overflow. For that purpose, we'll be using that the one more XOR gate here. So what is the operation of this one is, and here this is, say for example, if M is equal to 0, then this overall circuit which will perform addition. So that we can call it as parallel adder, which will act as a parallel adder. Suppose when M is equal to 1, which means your first carry input, that becomes 1. So just now we had just discussed what is subtractor. When carry input is equal to 1, and at the same time the second add and value which is given to the XOR gate, so there it is taking into the complement. Suppose if it is by means of 2's complement and then adding of both the values, then it is nothing but subtractor. So I'll repeat. So when M is equal to 0, the circuit which will perform addition. So in that case, we can just call it as parallel adder, which will act as an adder. Suppose if this M is equal to 1, then this circuit which will perform the subtraction by means of 2's complement. Okay, so in that case, which will also called as subtractor. So which means, and by using this single circuit, we can just perform both addition as well as subtraction. So that is why this circuit is called as parallel adder subtractor. Okay, so I hope you understood this concept. Thank you for listening. Thank you.